So again, what is the specific heat of a 3-gram object that has 80 degrees temperature change? 1,700,000 joules are applied. So we're looking for specific heat C. Mass is 3 grams. Delta T, temperature change is 80 degrees Celsius. And the heat transferred, 1,700,000 joules. So Q equals MC delta T. So 3 times 80 is 240. I'm going to divide that 240 to both sides. And I get C equals 7,083.3. You can write this in scientific notation if you want, but you don't have to. And the unit is joules per gram degree Celsius. For specific heat, I'm not too worried about the unit for that one. But you should know the other units. Mass is grams, temperature change is degrees Celsius, and Q is heat.
It's what?
Q is heat, joules.
If you get a number, it would be like 20 heat.
20 joules.
Oh.
Sorry.
I was like, what?
Okay, so that should give you the first one there. All right, any questions on this one? Any questions on 10? All right. Number 11, find the temperature in Celsius and Kelvin for a room at 75 degrees Fahrenheit. Again, I will bold the things that need to be converted. This one tells you to convert, so it should be obvious. But in case it's not, I'm underlining, I'm bolding the 75 so you know which one to convert. So you need to figure out the temperature in Celsius and the temperature in Kelvin. Okay, so go ahead and try that one. Fahrenheit. So first thing we need to do is go from Fahrenheit to Celsius. So here's my conversion for that. So Celsius temperature equals 5/9 times the Fahrenheit temp minus 32. So 75 minus 32 is 43. Gives me a Celsius temperature of 23.9 degrees Celsius. Okay, now that I got the temperature in Celsius, I need to find the temperature in Kelvin. All you have to do for Kelvin is add 273 to the Celsius. So Kelvin is Celsius, 23.9 plus 273. Gives me a Kelvin temperature of 297 Kelvin. 999?
Actually, I think it was 8888.
Oh, okay. Yeah.
We'll take it.
Okay. All right. So that takes care of number 11. Any questions on 11?
No.
Okay. All right. Average velocity for an oxygen molecule, there's the mass of oxygen at 297 Kelvin. So the first thing to do is figure out what equation we want to use. There's only one equation that has velocity and temperature, and it's this one. K equals 1/2 mv squared equals 3/2 kg. It's the only equation that works. For this equation, what confuses people is that there's two equal signs. All you have to know about the two equal signs is that you ignore one of them. So this problem is talking about velocity and temperature. So I need the velocity part and the temperature part, and don't need the kinetic energy part. Now, that's not always going to be the case. It may be sometimes that you need the energy part and you don't need temperature. Or you need the energy part and you don't need velocity. But in this case, I don't need the energy. I just want the velocity and the temperature. So we've got a, what is the average velocity? So what's V? Has a mass 5.3 times 10 to the negative 26 kilograms. Temperature of 297 K. I didn't bold either of those, so you don't need to convert anything. Mass should be in kilograms. Temperature should be in Kelvin, so that's totally fine. And then we just plug in. So 1/2 m v squared equals 3/2. K is a constant, and here it is, 1.38 times 10 to the negative 23. Times T, which is 290s.
But you don't change that to Celsius?
Correct. Leave it in Kelvin. So the only thing that needs to be in Celsius is this one. This Q equals MC delta T. That's the only one that needs to be in Celsius. The rest of them should be in Kelvin. And I didn't bold it, so you don't need to convert it. Okay? So half of 5.3 times 10 to the 26 is 2.65 times 10 to the negative 26 v squared. And then you get 3/2 times K times T. That gives you 6.1479 times 10 to the negative 21st. Divide that by the 2.65 times 10 to the negative 26th. And we get a velocity squared of 231,996.2264. I'm going to square root that to get just the velocity. And we get a velocity of 481 meters per second. So if the temperature is going to be 297 Kelvin, then the velocity of the particle needs to be 481 meters per second. So temperature of 5 moles of gas increases by 50 degrees Celsius. So first of all, this needs to be in Kelvin. All you have to do to go from Celsius to Kelvin is add 273. So this would be 323. And you don't have to memorize that. It's up here. Celsius plus 273 is Kelvin. So you don't have to memorize it. Bless you. So we got 273 Kelvin for the temperature change. And so what we have is the N, the number of moles, 5. We've got the temperature change, delta T. The temperature goes up, so it's positive. 323. And what is the change in internal energy? That one's delta U. That's a hard one to remember. So just be careful. Make sure you remember what that symbol is. So up here, change in internal energy. That one is this one, 3/2 nRT, nR delta T. So we got delta U equals 3/2 N R delta T. And by the way, you don't have to memorize R. Here it is, 8.314. And you just multiply everything. Gives me delta U to be 20,140.7 joules. You can put that in scientific notation if you want, but you don't have to. All right, that gives me how much the energy changed by. So now we know how much the energy changed. All that's left is to figure out how much work was done. So here's the key. It said no heat. That means Q equals 0. Remember, heat is joules. Heat is Q. So no heat, that means Q is 0. This is talking about the first law of thermodynamics. It's talking about work and heat and energy change. That is this one up here. Q equals delta U plus W. So Q is the heat transferred, 0. Delta U is the internal energy change, 20,140.7. And W is what we were solving for here. So I subtract the 20,140.7 over, so I get work equals negative 20,140.7 joules. So let's make sure this makes sense. So first of all, does it make sense that I got that big of a number? Yeah, I had no heat transfer, so the work done must be based off of the energy change. Second of all, does the negative answer make sense? Well, my heat transferred in or out is 0, which means no heat got added, no heat got removed. So if the internal energy changed, it had to change because of work done. Well, the internal energy went up. So I had to I had to increase my internal energy. Well, how do I do that? I increase my internal energy if I do something to it. In this case, it would most likely be squishing it down. Okay? If I squish it down, that's work done on the gas, and work done on is negative. Work done by is positive, work done on is negative. So we get a negative 20,140.7 for the work. That makes sense based off of what we know. So this answer makes sense to me. Don't forget about this that we did in the lab, PV equals nRT. Okay, so none of these are confusing. N is moles, we've talked about that. R is a constant, we've talked about that. T is temperature, P is pressure, V is volume, nothing weird there. Just make sure you know what to do with this. This kind of a problem would be very similar to this kind of a problem, where I just give you the numbers and you got to solve for something that's missing. None of that is really particularly troublesome or tricky. The one thing that can be is this phrase here, STP. So we've talked about this. STP stands for standard temperature and pressure. And what you need to know about that is that the standard temperature is 0 Celsius. The standard pressure is 1 atmosphere. However, those are not the units that you need. Temperature needs to be in Kelvin, except for on that Q equals mc delta T equation. And pressure needs to be in pascals, which is what we used last unit. However, you don't have to memorize those numbers. You need to know this. Temperature is 0 Celsius, pressure is 1 atmosphere for STP. You need to know that. You don't need to know the other numbers because Celsius is 273 plus to get Kelvin. Okay, so that means 0 plus 273. So that would be 273 Kelvin. And I give you the atmosphere pascals relationship here. 1 atmosphere is 101,325 pascals. So you don't have to memorize that. It's on your test. Just make sure you know temperature and pressure. Okay. Any questions there?